Welcome to the second talk today. So the next talk is by Makrand, and he's going to tell us about separation of quantum and classical using the k-fold correlation function.
Right. Can everyone hear me?
Yes.
Right. So this talk is partly based on work with Nikhil, who is somehow convincing me to give all the talks, and he's not here. And I say partly because I thought it would be nicer to do a survey of all the ideas that go into it. So I'll mostly not be talking about what we did. There's only a small part about it, but just how this line of work evolved. I wanted a friendly title for this talk, so I don't know whether this, achieves that goal. But if not, I asked ChatGPT to generate another title, and it's really, really good. So it should. This will be the unofficial title for the talk.
So Nikhil doesn't endorse this?
I don't know. Nikhil is in Germany, so he probably.
What's the title? Was the prompt or the entire lecture? What? What was the prompt to ChatGPT? Just the title or the entire lecture?
Just title. So I gave it the previous title and asked to generate a new title. All right. So this whole line of work is sort of motivated by understanding this big goal. Like in what ways quantum computing is more powerful than classical computing? What are the problems that are easy for quantum computers but hard for classical ones? And it's a very, very big goal. And today, this talk, we're going to look at this goal through this problem that let me call it for k-fold Fourier correlation for now. And as complexity theorists, we like to abbreviate everything. So let me just call it k-fold correlation, which is the name that Scott and Andres gave it when they came up with this in 2018. And sometimes for some results here, you can also consider variants of this problem or compose with the other functions, which is what this and friends refers to. So before telling you what this problem is, let me just tell you a little bit about the context. So this problem is something that's very efficiently computable by quantum algorithms. So I'm not going to go too much into what the model is for quantum computing, but you can solve it with just k over 2 queries. So k is just a constant in the stock, so 2 or 3 or 100. So it doesn't depend on the input size. So if k is 2, you can solve this problem with one quantum query. And not only that, this problem is also like BQP complete. So it's not in just some number of queries, but in terms of running time, also you can efficiently solve with a quantum computer. So with regards to the previous question of separating quantum versus classical, there are two distinct goals. One is to show that there is a quantum algorithm for a problem, and the other is to prove lower bound for classical algorithms. And in this case, we sort of know that this problem is easy for quantum computers. In fact, it's sort of BQP complete, so it's sort of like the canonical easy problem for quantum computing in some sense. So it's sort of proposed as a candidate for many quantum classical separations. And it has been used in the last 5 years to prove some very interesting results. For instance, most people have probably heard of this oracle separation for BQP and PH by Aaronson and Ambainis. And for that, it's used as a base case, like twofold correlation problem. In my paper with Nikhil and also this parallel work by Sherstov, Starozenko, and Wu, it was used to show that to show maximal separation between quantum classical query complexity and communication protocols. In another paper by Aaronson, Ambainis, and Kretschmer, it was used to show some weird oracle separations that are hard to understand. And recently, in a joint work with Kretschmer, Kian, and Ambainis, we sort of used it to show an oracle separation between classical cryptography based on one-way functions and quantum cryptography. So this problem is sort of very useful for proving separate quantum classical separations, and in some cases even separations for quantum complexity classes. So essentially, that's all I'm going to tell you about the context of this problem. There are many interesting quantum reasons to consider this problem. But this talk will be about how to prove classical lower bounds for this problem. And in fact, we're going to prove a very general result in terms of the Fourier spectrum of a computational model. Recall that if you have any computational model on the hypercube, you can always write what it computes as a polynomial of as a multilinear polynomial indexed by subsets of 1 through n. The coefficients of these polynomials are the Fourier coefficients, and the monomials are just products of all the bits that occur in the set. So the only fact about Fourier analysis probably you need to remember in this talk is that if your function is Boolean or bounded, then the sum of squares of all these coefficients is at most 1. Possibly that's the only thing you would need. And what we prove in this talk will sort of generalize to decision trees, parity decision trees, AC0 circuits, many different models. All we need to understand is their Fourier spectrum in some way. Sort of to prove this lower bound, there's sort of two different concepts that come in, two different ideas. The first is the idea of Fourier growth, which is also useful in pseudorandomness and learning theory. And if you were here yesterday in Puya's talk, you design like fractional PRGs. And the second idea that comes in that's also very interesting is the idea of pathwise analysis or stochastic process analysis of Boolean functions. And this is also, I mean, there's a whole reading group on it. So if you want to learn more, you should come to the reading group. So the plan for this talk will be to introduce what k-fold Forrelation is, and then to show how these ideas come in to prove this lower bound. So let me tell you what this k-fold Forrelation problem is. So it's sort of a weird problem if you haven't seen it before, but hopefully by the end of this talk it would make sense. So the input to this problem is kn bit string, which is partitioned into k parts of n bits. And the Forrelation of k is defined to be a particular degree k polynomial that I'm going to tell you about in a second, that takes values between -1 and 1. So this outputs a real number. It's not a decision problem. So to convert it to a decision problem, we'll just do the usual thing. You just take threshold. So the value of the polynomial is close to 0, then we'll say the function output rejects. If the value of the polynomial is far from 0, we say it accepts. So this is a promise problem based on the value of this polynomial. And for this talk, I will just mostly focus on the case of 2 and 3, and tell you what this polynomial looks like in these cases. So for 2, input is like 2n bit string. The first part I will call y, x. The second part I will call y. So these are n bit inputs. The Forrelation is basically this bilinear form, which is given by, so you take your, how do I? So you take your vector y, which is the length n plus minus 1 vector. You multiply it with the matrix, which is the Hadamard matrix, also the Fourier transform matrix. So it's an n by n matrix where n is the power, so where all entries are plus minus 1 over square root n. It's orthogonal matrix, so just a rotation. And so basically, once you apply, and then you take the inner product with this other vector x after some normalization. So to justify the name, sort of, if you consider your vector y as a truth table of a Boolean function, then h of y is the Fourier transform of that function. And what you're measuring here is like how correlated is the one particular function x correlated with the Fourier transform of the other function y. And it should also be easy to see from this form that this function always takes values between -1 and 1. Because if you take the vector x over square root 10 and y over square root 10, these are unit vectors in Euclidean norm. And this is a matrix whose operator norm is at most 1. So it outputs number between -1 and 1. And it, let me just expand this out. So if you expand it out in terms of the monomials, this is what the polynomial looks like. So it's a degree 2 polynomial. Xij, Yij, and the entry of the matrix. And it might be easier to remember this graph theoretically, which might be important for rest of the talk, to sort of consider this graph picture. So you consider a bipartite graph, you label the monomials on the left with X, monomials on the right with Y, and you add the label Hij on this edge. And so for every edge, you multiply all the labels, that gives you one monomial in this polynomial, and you sum up all the labels. So, and one thing that will not be very important, but I would like to point out here, is that you can replace this H with any orthogonal matrix. You get some different polynomial, and that gives you a whole class of functions to work with in this talk, which is what this and friends refers to. So any questions? Now this is a weird polynomial.
Is the H should be 2 to the n by 2 to the n?
Yeah, yes, n is a power of 2. Yeah, always in this talk.
But if you replace it with identity, then the problem becomes suddenly easy, right? So there is something about.
Yeah, it's easy. Yeah, but I'm saying that you can get a family of instances. Not all of them may be hard for a classical thing. Not all of them may be efficiently computable by quantum algorithms. The goal is to sort of say whether when the value of this polynomial is close to 0 or far from 0. So let's just try to understand this a little bit. So if you pick like uniform distribution of the inputs, x and y are uniform, the expected value of each monomial is 0. And you can sort of show that the variance of this polynomial is very small. So typically this polynomial is very, very close to 0 when you pick uniform inputs. Let me try to give you another distribution which takes large values in the green region. And for this, just try to compute the expected value of this polynomial under a new distribution. But for now, I will just pick x and y to be, instead of bits, I will pick them to be Gaussians in n dimensions. So as follows. So you pick x and y to be 2 n-dimensional Gaussians. So Gaussian in 2 n dimensions. The left and right side will be independent, so there is no correlation between the vertices on the left, the coordinates on the left, and the coordinates on the right. And in between, the correlation is exactly what's the label of this edge. And why am I picking Gaussians here? Because for Gaussians, if you know their mean and covariance, you basically determine the distribution. So you don't have to worry about higher order correlations. So essentially, this determines the distribution. Now, if you compute the expected value of this polynomial under this green distribution, the expectation of xi and yj is just hij, and each entry is 1 over square root n. So the expected value of this polynomial is 1. So I've cheated so far because I've plugged in values that could be much, much larger than 1. So here, the next idea that's probably we're very used to in TCS is the idea of rounding. So you can take like the sign of the Gaussian or do other kinds of rounding, and you can still show that the value of this polynomial is kind of very, very large in expectation. The thresholds here will just be some constants in this talk. Okay, any questions? Okay. So this is a two-fold correlation problem. Let me tell you what the three-fold correlation problem is. And I will stop after that. I will not go to four-fold. So now the input is a 3n-bit string, x, y, z. And the polynomial is sort of looks like this. It's hard to just read it off from the expression, but a graph theoretic picture is actually much easier to explain. So now you have 3 sets of variables. It's a tripartite graph. Label the variables x, y, z. You put the labels hij on the edges. And for each path from left to right, you multiply all the labels and you add up. That gives you monomial and you add them up. So that's what this polynomial is. And this polynomial is also bounded. And now the goal is to decide between these cases, the red or green. And so again, the uniform distribution is very close to 0, even for this polynomial. Let me tell you a distribution which takes large values. So a little bit non-trivial to describe, because if you pick the distribution we had previously, you picked x and y to be some correlated Gaussian according to this this structure, and if you pick z independently, then the value of this monomial will be 0. So you need to enforce that each path is sort of correlated. And in order to do this, we'll take two Gaussians with these copies. So x and a will be Gaussians with correlation x hij, and b and z will be Gaussian. And in the middle, you will glue these Gaussians together by taking pointwise products. So you have a 2n dimensional vectors, you take pointwise products, and that will give you y. So it's sort of, and now you can compute the expected value of this polynomial. This yj will split into aj and bj, and the expected value of this polynomial is still again 1. And if you want to get distribution on bits, you again do the usual trick of rounding. It will give you large values. So for the rest of this talk, you can sort of think of this problem as distinguishing these two distributions. One is the uniform distribution, and the other distribution which takes large values for these polynomials. I will call it correlated or Fourier correlated. And you can think of this as just the problem of distinguishing these two distributions with your computation model. Any questions?
So just to make sure I understand, X, A, B, and Z are all Gaussians?
Yeah, so X and A are correlated Gaussians. The X coordinates are independent, A coordinates are independent. In between, just like the same thing as previous thing. B and Z are independent copy, and you would glue them together.
I would have guessed to see a H sub Ki as well.
A sub Ki.
Just for full symmetry, rotation symmetry in these coordinates. Is that just like not interesting for some reason?
Yes, probably not. Yeah, I think you can probably, that doesn't add anything. It doesn't add any hardness to the problem. So we come to the next part of this talk. I'll define this problem. Hopefully you're clear on what this problem is. How do you prove classical lower bounds in terms of the Fourier spectrum of this function? Well, it's a little bit abstract. So let me set a concrete goal for this talk, which will be to prove sort of that any decision tree or even a parity decision tree for this problem makes n to the 1 minus 1 over k queries. So decision tree model is sort of, it's a following computation model. You query a bit of your input. Depending on its value, you choose another bit to query until you hit one of the leaves, and you output whatever is written on the leaves. In parity decision tree, you do a similar thing, but you're allowed to query parities instead of just bits. And so this model, the parity decision tree model, is more powerful because you can always just query single variables here. But the same bounds holds for both of these. Okay. And in this model, sort of you can compute any function if you query n bits. If you query the entire input, you can compute any function because you know this value. So n is the maximal amount of queries you need to compute any Boolean function in this model. So here, n to the 1 minus 1 over k, when k is 2 square root n, and as k grows larger and larger, it becomes closer and closer to 1. So you need like maximal amount of queries in order to solve this problem. That's what this result says. And this is in some sense the best possible result you can prove. So this is the best possible separation between quantum and classical. But if so now you can just remember that there is a randomized algorithm that matches the same upper bound. And in this approximate equality, I'm hiding polylog factors, which I will do the rest of this talk. And the decision tree result here was proven by in my paper with Nikhil, but also for a variant of this problem by Sherstov, Sorozhenko, and Wu. And the parity decision tree result follows from the theorem that we're going to see in this talk, and a result by Girish, Tal, and Wu on the Fourier spectrum of parity decision trees. Yeah. So it also holds for randomized decision trees and randomized parity decision trees. Yeah.
Oh no, I mean the tree. Yeah. Could you say something about
the normalization? The normalize the 1 over n or the rounding? Sorry, I don't follow what you mean by that. I mean the rounding or the normalization is so that the value is between -1 and 1, and the rounding, these thresholds are always going to be some constants that are a little bit far apart. It might depend on k, but for k equals 2 and 3, it will be some constant. So here. And Okay, again, I just wanted to mention the parity decision tree result because it follows from the theorem we're going to look at, but mostly I'm going to focus on just decision trees. It's probably the simplest classical computational model you can think of. And if you view this, the function that's computed by a decision tree as a Boolean function, as a polynomial, the degree of that polynomial is the number of queries that this decision tree makes, or the depth of this polynomial, of this tree. So to prove a lower bound, one very nice concept that comes in is the concept of Fourier growth. So you need some way of distinguishing the k-fold Forrelation polynomial. For instance, if k is 3, this is just the degree 3 polynomial. And what I said before is you have a very huge decision tree whose degree is possibly polynomial in n. So why can't it compute this degree 3 polynomial? And so you need to find some sort of difference, property that differentiate these two things. And one possible property you can hope for is that this is a very dense polynomial. It has all possible monomials you can think of with some coefficients. Now, on the other hand, if you look at a decision tree, let me call this function f, the corresponding function that it computes. You could hope that, okay, even if this computes like a degree n polynomial or degree almost n polynomial, it sort of computes a sparse polynomial in some sense. Because if it does, then okay, possibly there is hope of differentiating these two things. And one proxy for sparsity often is sort of the L1 norm. So if the L1 norm of your Fourier spectrum is small, in the sum of absolute value of your Fourier coefficient is kind of small, then you can say that your polynomial is sparse. But here, this Fourier growth concept is a sort of more refined version of that. Instead of looking at the entire Fourier spectrum, you just look at each level L, consider all monomials of degree L, and you look at the L1 norm of that. So the sum of absolute value of Fourier coefficients at level L. We'll call it the Fourier weight at level L. And so if this Fourier weight is small, you're basically sort of sparse in some sense. And one basic fact to remember is that the Fourier coefficient is just the value of the derivative evaluated at 0. And so this is, if this quantity is small, it's also saying that the Lth order derivatives are sort of small. So, I mean, just for sanity check, let's make sure that these two quantities are very different. So if you consider this k-fold correlation problem, so this k is not the index anymore, it's the weight k is for the k-fold correlation. Its Fourier weight is quite large. On the other hand, the kth level Fourier weight of the decision tree, as we're going to see later, sort of scales as the number of queries it makes, so the depth to the power k over 2. So if the number of queries is very, very small, then you're going to have a big difference. So there is a huge gap there. So that's it passes the first sanity check. But the degree of this polynomial on the right can be very large. So what about higher Fourier levels? Why don't they help us? And so this will become clear in this slide, hopefully. So how do you use this to prove lower bounds for this problem? So recall that our goal is to show that our decision tree cannot distinguish these two distributions, uniform versus correlated. So let f be whatever function the decision tree computes. If it cannot distinguish them, then the expected value under these two distributions should be very, very small. So it shouldn't be able to tell these values apart. The expected value under the uniform distribution is just the constant Fourier coefficient or the constant term in a polynomial, because all the other terms go to 0. So you can write it as in terms of the Fourier spectrum as the Fourier coefficient times the expected value of this monomial under this distribution, which is the moment of this distribution. Let me just take absolute values here everywhere. And let me now also, for each L, pick out the maximum moment you can have at that level. So you get this expression. Now you can see that the first term here is actually the Fourier weight at level L. And the second term here is the maximum moment you can have at level L. So now if your moments decay fast enough and your Fourier weight doesn't increase fast enough, hopefully you can bound these two quantities. You can prove that this quantity is small. In fact, this approach, you can make it work if you consider random variants of correlation. Instead of the Hadamard matrix and the definition of correlation, just pick a random orthogonal matrix, then its moment decay fast enough, and you can use this approach to prove something. But to prove optimal bounds, as you're trying, you need very, very sharp bounds for all levels of decision trees, not just constant levels, but literally all levels. Yeah.
Does it make a difference if the matrices in kind of these different layers of this graph are the same or different?
Yes, not really. Yeah, you can take them to be all the same. And yeah. So shown by Avishai that sort of the moments decay, and he managed to prove sort of not tie bound because it needed a very sharp bound for the Fourier spectrum of decision trees. That was proven by Scherz-Stafter and Wu. Together, if you combine these two things, you obtain the bound we're aiming for random variants of this problem. Okay. But this doesn't work for correlation because this maximum moment doesn't decay for correlation. It can be 1. So the moral of the story, which is going to be the next slide, is sometimes exact computation is helpful. So sometimes even if the distribution here, which is a complicated distribution because it's enforcing how the pairwise correlation look like with this Hadamard matrix, yeah. So you can still compute it exactly, this quantity. And to do this, we'll call this very catchy title that was coined by Makrand called the smart path method. And instead of proving this directly, you will sort of slowly interpolate between these two distributions. And this is where it connects with today's theme, beyond the Boolean cube, I guess. But today we are going to go inside the Boolean cube. You will slowly interpolate between these two distributions in some way. And so your sort of goal is to show that as you interpolate between the uniform distribution at time 0 to this correlated distribution at time 1, in between you have some other distribution, your quantity, your expected value doesn't change much. So you want the values at the endpoints of these two things. You want to show that they are close. But instead of doing that, what Makrand's sort of philosophy is that you can find like a smart path, not a dumb path, but a smart path, where the derivatives are sort of small along this path. So if the derivatives are sort of close to 0, then you don't move much, and you can sort of show that the expected value doesn't change. And how you interpolate between them is a thing we're going to answer later in this talk. So, any questions? So, the main theorem, that's sort of part of this talk. Sort of somehow, if you do this interpolation and try to compute things exactly, then even though the polynomial f has very, very high degree terms, all of the high degree terms sort of cancel out. And what's left is for k equals 2k, the advantage of how you can distinguish, it only depends on the level 2 Fourier weight. So only on the L1 norm of the level 2 monomials divided by some square root n. So this was proven by Aaron and Avishai. And for higher k, this is proven in my paper with Nikhil. So now the advantage doesn't depend on just the level 2 Fourier weight, but only a small number of levels. For instance, for k equals 3, it sort of depends only between levels 3 and 6, and the contribution progressively decreases. And for k greater than 3, sort of depends on the first k square levels, and k is a constant, so it's not a lot. And if you see this asterisk, which I don't know if you can read it, it says ignoring some lies, which I'm telling you. So I've stated the nicest possible version of this theorem, but there's some log factors that are missing, and this is not the Fourier weight of f, but the Fourier weight of any restriction of f. So, but we can bound it in the same way. So if you followed this so far, I think conveyed the main message of this talk, and the rest of the talk will be about going into more into these ideas and how to use them in this scenario.
Maybe it's a good time to pause and just say that you can apply this to any model that you believe has small
Exactly.
weights up to constant level.
Yeah, exactly. So all these theorems only depend on the Fourier weight here of the spectrum of your computational model. So we can basically use it to prove any separations. And since we know that correlation is easy for quantum computing, I guess the more powerful computational model you can analyze and bound the Fourier spectrum, the better separations you can get here. Yeah.
Do you know if the k-square is necessary?
Yeah, so we don't know whether k-square is necessary. Possibly that you can get only the level k weight for each of these. We don't know. We don't know how to prove it.
So this is for a fixed matrix or for a random one?
Oh, this is for the Hadamard matrix, a fixed Hadamard. But it also works for any random matrix as well.
Okay.
So all you need is the entries of the matrix are small. The entries of the Hadamard matrix are 1 over square root 10, but if you pick any orthogonal matrix, its entries are roughly the same. So that's all you need.
How do these normalization why is it different order for different weights?
You see in the proof, but sort of the Fourier weight at level L, it depends on L, so it grows with L. And so you really need like to show that they matter less and less as you go to higher and higher level. But it's really difficult to bound how a higher level Fourier weights. And so that's why in this case they all cancel out, so you don't need them. So that's fine. And also their contribution also for the symmetry. Any more questions? Okay. So if you follow it until now, let's go into some more insights into these ideas. So let's look at how do you bound Fourier growth of a decision tree. And again, I'm not going to go too much into this talk because it probably doesn't fit today's theme and I don't have enough time. But there is going to be talk about this thing in the next workshop. So you can come to that if you're interested. It's quite a non-trivial task to prove Fourier growth bounds, even for very simple models, for higher levels, basically. So let's look at a decision tree. It has mixed D queries. It has depth D, and it computes the degree at D polynomial. Fourier weight of level L is just the sum of Fourier coefficients in absolute value. And let's just do a very naive thing. Let's just do Cauchy-Schwarz. So n choose L monomial, so just Cauchy-Schwarz will give us this bound. And as I said before, the sums of squares of all coefficients here is at most 1. So you get this very trivial bound of n choose, square root n choose that. So it turns out that so far we haven't really used anything other than the fact that the function was almost bounded. It turns out that this is roughly close to the maximal Fourier growth you can have. Because even if you consider k-fold correlation, it's a degree k polynomial, but sort of Fourier growth roughly matches this up to maybe some square root n factors. So it's a very, very large quantity if you don't assume anything about your computational model. It can be computed by very low degree polynomials even. For decision trees for level 1, I mean, it turns out that the Fourier weight is roughly square root of the depth. So the depth is small. This is very small quantity. Just proven by Ryan and Rocco in 2007. For all levels, I wish I proved this bound, which is square root d to the L times some polylog factors, which can be pretty large since n can be 2 to the d. Your depth can be much, much smaller than the number of variables you have. This bound is pretty good for low levels, but it kind of becomes not very good as you increase L. Lastly, the optimal bound was proven by Scherstausser, Zheng and Wu, who sort of showed that instead of square root d to the L, you can replace it by a square root d chooser, which is optimal for all levels. So the last bound is sort of a very sophisticated proof, kind of requires very complicated decomposition of your decision trees. And even though it's a very simple model, kind of pretty challenging to prove. And let me make 2 remarks about this. First is that all these bounds also hold for randomized decision trees. Because a randomized decision tree is just a convex combination of classical decision trees. And this quantity is sort of convex in some sense. So all these bounds proven here also work for randomized, also give you randomized decision tree lower bounds. And secondly, the first 2 bounds here, they also sort of, you can also prove matching lower bounds maybe ignoring the log dependence, which for even stronger models like parity decision trees. But we don't know the optimal bound for parity decision trees for all levels. And that's a nice open problem if you want to think about it. Although for application to these lower bounds that we are going to talk about here, not needed. We need small level bounds. Okay. Any questions? I think that's all I'm going to talk about Fourier growth here. And I'm going to move on to the theme for today, which is pathwise analysis, and give you some flavor of what goes on in the proof. Let's just consider how does pathwise analysis come into proving lower bound for the twofold case. Our goal is to distinguish the uniform distribution from the correlated distribution by finding some sort of interpolating path between these two distributions. So let me just remind you what the correlated distribution was. You picked X and Y to be Gaussians, which were independent on the left and right, and in between there was some correlation given by this entry Hij. It was generated, and so if you look at the covariance matrix of this Gaussian, it sort of looks like this. You have identity in the left and right block. These are the n-dimensional identity, and you have Hadamard matrix, which has small entries in the off-diagonal blocks, and you round it in some way to the hypercube plus minus 1. This was the correlated distribution, and to interpolate, it would be very useful to view the uniform distribution on the hypercube plus minus 1 as being generated in a similar way. So let's just pick standard Gaussian, so 2 n-dimensional Gaussian, which is independent in all coordinates. And each coordinate has variance 1. And you apply the same process. First sample a standard Gaussian, and then you round it to the hypercube, for instance by taking sign or whatever you're doing here. And this generates the uniform distribution on the hypercube. So these two things look very similar. Now, we want to understand what the expected value sort of looks like, the left and the right cases. Now, this suggests a very natural way to interpolate. You sort of, at time t, you sample a Gaussian whose covariance is a linear interpolation of the two covariances. So at time 0, the covariance is covariance on the left. At time 1, the covariance is covariance on the right. And in between is some linear combination, which is straightforward linear combination. So d of t is some Gaussian, and then you round it again. So that gives you some distribution that sort of interpolates between these two things. Any questions about what the distribution is? Okay. And so how do we analyze, what happens in this path? And for this, a very nice tool that comes in. It's called Gaussian interpolation. Let me explain it a little bit more generally, give you some example to make it concrete, because that's probably more useful. So suppose you have two Gaussians, X and Y. You want to interpolate between them by linearly interpolating their covariances. So at time t, I will call the intermediate Gaussian to be u of t. Okay. The Gaussian interpolation formula sort of describes how the derivative along this path, the time derivative, sort of looks like. It's sort of, the expression is sort of a bit unwieldy, but so let me try to help you parse it. The derivative, and h here is some arbitrary function. The derivative here sort of looks like summation over all. So it's an n-dimensional function, summation over all ij pairs in n. The first quantity is how the covariance in that pair of coordinates changed from the initial to the final. So sigma final is the final covariance, sigma initial is the initial covariance in that particular coordinate. The first thing is the covariance difference, and the second thing is the expected value of the second derivative. So now, you might think that, okay, all I have done here is like, there was some complicated expectation we want to compute, now related to another complicated expectation of some derivatives. So why is it helpful? But sometimes the derivatives of your functions are well behaved, and then you can use it in the coordinates where the covariance difference is small, and then you can get much more mileage out of this. So let me just give you sort of a standalone example to illustrate it and make this a little bit more concrete. The example is a basic version of Slepian's lemma that we are going to prove with this formula. X and Y be Gaussians in Rn. So they're not standard Gaussians, they have some covariance structure, but they're, let's say, mean 0. And what we're going to assume about these Gaussians is that their variance in each coordinate is the same. So the diagonal entries of these covariance matrices are the same. And the off-diagonal entries of y's are bigger than the off-diagonal entries of x. So y is sort of more correlated than x. For instance, x could be just a standard Gaussian and y could be, the Gaussian which is more correlated. Fleppian's lemma says that the expected value of the maximum of these x's is sort of always bigger. So the infinity norm of the x Gaussian in expectation is always larger than an infinity norm of y. And the interpretation is that the more correlated is your Gaussian, sort of the smaller is the expected value. Is the statement clear? The very powerful lemma, it's used to compare different Gaussian processes all the time. We're going to see a very short proof of this using this Gaussian interpolation. So first of all, this max is not a differentiable function. So let's just replace it with some sort of soft max function, just this log of summation over e to the beta xi normalized by 1 over beta. So this is some approximation to the max function. As you increase beta, this function actually converges to the max of each coordinate, because the maximum coordinate will give you the most value, most contribution to this. The only thing about this function that we're going to use is that consider off diagonal derivatives, partial derivatives with respect to different coordinates i and j, then it's less than 0 at all points. If you compute its derivative, which I'm not going to do here, you can see that this is true. And now let's just try to apply this formula directly. So we interpolate between these two Gaussians, x and y, using this linearly interpolating the covariance, and the expected value of the derivative at a midpoint is sort of given by this formula. First thing is the difference of the covariance. And note that the covariance of these two things, the diagonal covariance entries, their difference is 0, so they don't matter. And the off-diagonal covariance entries, you get the difference times the expected value of the derivative. And we know that the derivative at all points is not positive, so it's at most 0. And we know that the y is more correlated, so this quantity is at least 0. Basically, this derivative is always negative or not positive. So as time goes on, it's like a monotonically decreasing function, and its value at the end is smaller than the function value at the end is smaller than the function value in the beginning. So expected value of f of x, which is the value at the beginning, is sort of larger than the expected value of f of y. Any questions? This is one simple example of this thing, and I don't know how many of you are in the reading group, but you can use it to prove sort of very powerful results. You can use it to prove Gaussian concentration. You can use it to prove this Gaussian correlation inequality, which was open for more than 50 years, just by using this formula with a little bit of calculus. So hopefully this example makes it a little bit more concrete. How do we use it? And in this example of twofold correlation, again, sampling two Gaussians at the left and right, and you're rounding it by applying some function. You're again doing this linear interpolation. So you can apply this formula directly. Again, note that the difference of the covariance in the diagonal is sort of 0, because the diagonals are the same. So once you subtract these two matrices, all entries are 1 over square root 10 magnitude. So the difference in the covariance is 1 over square root 10. And with a little bit of calculation, which I'm not going to show here, you sort of relate the second derivatives of this h here, which is the function f after you apply this rounding thing to your Gaussian, to the second derivatives of your function f, maybe under some restrictions, and that sort of gives you this sort of lower bound, this sort of upper bound on this quantity. Okay, so now the Fourier weight is small, you get a lower bound on your classical model. Okay, any questions? So I've hidden some, there's some details here which I don't want to explain. And if you see this squiggly arrow, that's what it will mean.
Maybe the hint should be the second derivatives. You've seen earlier that the second derivative relates to this.
Yeah. So Yeah, so the Fourier weight is the sum of coefficients of the second level, which I said before is the value of the derivative, the second derivatives evaluated at 0. So that's how sort of these two quantities are related.
So this is true for any Gaussian with small correlations?
Yeah. So this is the two-fold case was proven by Brown and I wish I was in this polarizing random walk. Proof using Brownian motion sort of was given by Ginny Wu. Yes, this Gaussian interpolation makes it sort of pretty nice.
So here we also have the issue that the function is not continuous due to rounding.
Function is not. Oh, okay. The rounding we use is sort of uses a continuous function. So I'm hiding this under the rug because there's some details there. But you can use it with a continuous function. Or if you want to use the discontinuous function, you can use some Ito process and Ito calculus to sort of handle all that. So it works out there. But it's somewhat not really. Okay, so I'll tell you what the two-fold case is. We're going to talk only a few minutes about the threefold or higher level case because there's some details here which are very annoying to explain. But let me try just very briefly. So again, the uniform distribution was the uniform distribution here, and let me help you recall the Fourier distribution. So this was obtained by taking two Gaussians, two independent copies of the Gaussians XA and YB with the same covariance structure as before, the two-fold case, and taking the pointwise product. X will be the same as X, this X, Z will be the same as this Z. And in the middle, you will just take the pointwise products of these two things. So the distribution here is like product of Gaussians, and then you apply some rounding to it. And again, as before, it would be helpful to view the uniform distribution as being generated in exactly the same way by the same process. Now you take products of standard Gaussians, these two standard Gaussians, XA and BZ, and again you round it. And what you want to understand here, and our goal is to sort of interpolate between these two things. Our goal is to sort of understand this function, X and the Y is like the pointwise product of these two things, and Z. So this multilinear function applied on these two things, and how the expectations under these two distributions on the left and right, they differ. Now the first problem is when you take the pointwise product of two Gaussians, it's not a Gaussian anymore, so we can't really directly use Gaussian interpolation. The next best thing you can do is like you can view this as another polynomial in X, A, B, and C, because you're just doing some substitution to get the polynomial on the left. I'm writing it differently because the derivatives of these two polynomials might behave very differently. So that's why you need to be careful about this. But now with this P, you have a function of a Gaussian. So you can hope to interpolate. Now, if you do this interpolation I showed you before, just one-dimensional thing, sort of doesn't turn out to be very helpful for reasons that can't explain. So what you do is like you interpolate between this red XA and this green XA by one path, and this Y BZ and this red and green BZ with another path. So sort of like a two-dimensional linear interpolation, parameterized by different things.
Yeah. Repeat too much information. So it's as easy as a two-fold correlation because you have X and A, so you can ignore the B and Z.
Yeah.
So if you get A and B separately, then the problem cannot be harder than.
Yeah. Yeah. So what's the best way to explain it? But somehow, yeah, in this distribution, you're taking the pointwise product, and that's what's hiding the correlation. So you have to look at all of them together, able to tell what the value is. Why BZ? Which lower bound?
Lower path.
Oh, sorry, it should be B and C. Sorry. Yeah. Now, again, I'm going to be very sketchy about it. If you do Gaussian interpolation, you will get fourth order derivatives because you're doing these two different paths in terms of X, A, and B and Z. And now the whole challenge is to relate it to the derivatives of your function f. And the point here is that since you're taking pointwise products, if your indices sort of match up, then you get a third derivative of f if Z and K are the same here. because you can combine those two terms together to get a y variable. But if they don't match up, then how do you bound those terms? You need more cancellations there. So the goal is to sort of show that somehow the expectations differ by something that only depends on few order derivatives, maybe the 6th order derivatives. So somehow you need to get more cancellations, and if you try to leverage another tool that I'm going to tell you about, you can show that such terms also cancel out and give you these higher order terms that decay exponentially. Again, it's not easy to explain this because there's a lot of indices flying around when you try to write it down. So I'm going to tell you what the tool we use is and just give you sort of a standalone example that sort of illustrates the phenomena. The tool is one very unique property of the Gaussian distribution called Gaussian integration by parts. It's the following formula. If you want to compute the expected value of this Gaussian, f is a function of n variables, and g1 through gn are Gaussians, and g0 is also jointly Gaussian with them. And they're not standard Gaussians, they're arbitrarily correlated. And you want to compute this expectation on the left, which is expected value of g0 times f of g. Some complicated quantity, but you can still compute it in terms of like the expected value, the sum over all correlations of g0 had with each of the coordinates times the expected value of the partial derivatives given by I. So this is the formula. Okay, let me try to give you an example just to make sense of it. And this formula is really useful if g0, the correlation of g0 with each of the gi's is kind of small, and you have a bound on the derivatives, because then you can see that this gives you nicely behaved form. Suppose g1 through gn are some arbitrary correlated Gaussian, and g0 is just defined by the sum divided by square root n. The correlation between g0 and gi, the covariance entry is just 1 over square root n. We want to compute the expected value of this monomial, which is the product of all the g0s. And by this formula, this is 1 over square root n, which is the covariance, and the expected value of all the derivatives, which is the term where you remove just g0 and gi, basically. Sorry, gi here. Okay, so in this term, there is no g0 that appears. It's only a function of the rest of the Gaussian. So all you have done here is you've traded off your derivative for a 1 over square root n factor. And essentially, that's the same phenomenon that happens if you try to analyze the threefold correlation case. And let me just, as an aside, mention this very nice identity that you can prove using this Gaussian integration by parts. I'll leave this as an exercise, which you can try to prove. So the Gaussian distribution is uniquely determined by its covariance matrix and its mean. Let's assume the mean is 0. So you should be able to compute all its moments just in terms of the pairwise moments, because that's the covariance entries. And this mixed formula tells you how to do this. So suppose you have 2k Gaussians, then the expected moment of this thing is sort of given by, you take any perfect matching of these 2k coordinates, and you consider those pairwise covariances and add them up. And that gives you this moment. So this is what calls Wick's formula or Easterly's theorem. It's used in physics a lot. So you can prove it very easily just by induction and using this repeatedly. Hopefully that was we got something out of it. So let me summarize. So we saw that sort of the distinguishing advantage for your computation model F only depends on the low level Fourier weights, because the high level Fourier weights cancel out if you try to do this pathwise way. And now you can get stronger and stronger lower bounds just by analyzing the Fourier spectrum of your Boolean function. Sort of two important concepts that we saw were like Fourier growth and pathwise analysis that came in proving this lower bound. And hopefully you got a sense of how they're used here. And I mean, they have many other applications. As I said, Fourier growth is useful in learning theory, in pseudo-randomness, pathwise analysis, and Markov chain sampling and analysis on the Boolean functions. We will see in this workshop. So let me just conclude with some. These are not open problems, but open directions maybe. K-fold correlation is a very natural problem. It's sort of, in this talk we just looked at quantum classical separations. You can also use it to separate quantum complexity classes, like oracle separations. And there's possible many open problems there related to that you can try to explore with these methods. And the second is, if you want to prove better and better separations between quantum and classical, all you need to do is now to analyze Fourier growth, even low-level Fourier growth of your computation model, and this will give us better separations. Pathwise analysis is a very big field on its own, and for this, I will just end with this quote by Leonard Gross, who's the one who sort of introduced hypercontractivity in the 70s or something. How far can you go with Cauchy-Schwarz and integration by parts? Well, you can go very, very far. Thank you. Any last questions?
Questions from Makrand.
So you mentioned that we've seen some similar applications yesterday in Glasgow. Any application of this Cascadius method to
Well, like the polarizing random walk is sort of like a discretized stochastic process, so kind of similar. I think the discretization matters there because you need to really care about how much seed length you have and how quickly it converges. So I'm not sure there's thing, but it could be useful.
We have a different alternative construction for like the low degree.
So the construction that for fractional PRGs that only uses second level,
yeah,
it was basically based on this MDG random walks.
Yeah, that's true. So
random.
yeah, so you can use this as a, I guess, to construct some PRGs, this correlation problem. But I think you really have to discretize it, and the discretization matters. So that's more what I'm sure about that.
That's been spilled.
For the self-correlation, does it make sense to try to interpolate between the products of the Gaussian directly instead of interpolating the Gaussian and then applying the product?
So that would be great, but I don't know how to do it. So yeah, I think it makes sense, but I don't know how to do it. So I'll get that, but it could be possible. But maybe, I don't know enough about fields. And maybe one thing I should say is the K4 case is sort of similar. It's defined similarly, as you can imagine. People don't have questions. So either gave such a horrible talk that no one has any questions, or I gave such a good talk that no one has any questions.
Everybody's happy.
Very polarizing.
Okay, so let's take Makrand again. We'll be back after.